Hello everyone. Today we are going to see the topic trusses, and we'll see how to solve problem based on the trusses. Now I will not go in depth for the theoretical part because already I have discussed this theoretical part in my previous videos. So in this today's session we are going to see how to solve the problems of trusses by using method of joints and by using the method of sections. So basically there are the two methods available to solve problems for the trusses, that method of joints and second method is method of sections. Okay, now we'll see some of the steps for method of joints. I will explain you the complete procedure, as well as side by side we will take one example to just clear out that thing in more depth. Okay, now first of all I will just list out all the steps that are required to solve this problem by using the method of joint. Let us say this is the truss member given, and for that we have to calculate the forces in all members. So generally whenever it is asked that to calculate forces in members by using the method of joint, generally this method is applicable when we need to calculate forces in all members of the structure. And this method of section is generally applicable wherever some specific members are asked. Now let us say in this problem BD, BE and C, these are what the members in which whatever the force it is there that we have to calculate, then in that case we are going to use the method of sections. So this is only for the specific members. Before we proceed further, first of all, whatever the steps we are going to apply, the trusses are, there are the two types of trusses. First of all, whenever we are going to solve this problem, we have to check it out whether the truss is stable or not. If it is the stable truss, then only we can proceed with the solving that problem. So in the first step, we are going to first of all check. So to check the stability, we generally use the equation m is equal to 2j minus r. Now where this m is nothing but number of members, j is number of joints, and r is nothing but the number of reactions. So for the first step, always use this first checkup, that is the check the stability of this truss member. So we will take this example. In this example, suppose we have to apply this first step here, then according to this step, afterwards I will simply list out all the steps all together. As of now, along with this example, I am going to explain. So as for this particular member, if we have to apply this for step here, first of all list out the number of members. So that is m is equal to 2j minus r, that is number of members should be equal to 2j minus r. Now here number of members are 1 2 3 4 5 6 7 8 9. So altogether there are 9 members. Number of joints, so for the number of joints we can have this point A, B, C, D, E and F. So there are 1 2 3 4 5 6 joints minus number of reactions here. If you are going to replace this supported beam, or it is the suppose hinge support, there we are going to replace 2 reactions. For roller support we are going to replace single support or single reaction. Why it is so, that I explained in my equilibrium part, so you can just go throughout that part also. Either way, here you can just write it down. For roller support or for this hinge support, always show 2 reactions. For roller support there should be only 1 reaction. Okay, so now total number of reactions are 1 2 and 3. Now as we know, this total we just have to calculate this total. 9 is equal to 6 to the 12 minus 3, that is 9. So from this condition we come to know that this is what this stable truss, because it is satisfying the condition of stability. And now we can go for using these conditions of equilibrium. We are simply checking this stability just because after because for solving this problem we are generally going to use conditions of equilibrium. Okay, now the second step that we are going to use here, that okay, now in the second step we generally calculate the reactions. Once we are done with the stability check, then second step, calculate reactions at all supports using conditions of equilibrium. So if you are to use these conditions of equilibrium for this whole stress, we are going to use, in bracket you can just write down, for whole stress. Now whatever, these are the two steps which are common for method of joints and as well as the method of section. So here the three conditions that we have to apply, that is sum of all forces in x direction should be equal to 0, sum of all forces and sum of all moments about any point is equal to 0. Now first of all, if we are going to apply this first condition, that is sum of all forces in x direction is equal to 0. So once again I'm going to copy this figure. Once we are going to apply this condition of equilibrium, summation of all forces in x direction, students generally get confused with these forces which are shown in the structure. So always keep in mind that whenever we are going to apply any of these conditions, don't just get confused just by observation from this structure itself. Simply use whatever points are given and whatever the reactions and forces are there, that only you plot out and just see how we can just calculate this thing. Now for this case, suppose in this case what I will do, I will simply draw this figure and only the forces reactions on that complete figure. Now suppose this is what nothing but our point A and RA vertical, then at this point there's horizontal reaction RA horizontal reaction. Now somewhere here there's RB vertical. So only just observe the forces wherever that forces are acting and the reactions and points. Okay, so somewhere, so this is nothing but what our point A, this is what our point E. So this will become very easy for you to simply go along with this diagram. Now somewhere here this point B is there, and on this point B there's one force which is 1 kilonewton. Then somewhere here 1 kilonewton force is acting, and that is point D. Okay, and somewhere here 1 kilonewton and 1.5 kilonewton force is acting. So now whenever we are going to apply these conditions of equilibrium, we just have to, now we have to simply target only all forces in x direction. Now these are the only forces that you should observe. So whatever the number of forces in x direction and y direction, that only we are going to count into our calculations. Now for this number of forces in x direction, now there are 1 and 2. These are the only two forces which are in horizontal direction, and its sign convention you should take according to the coordinate axis. That is, forces acting along the positive direction of x-axis should be positive, and forces acting along negative direction of the x-axis, that should be negative. Now from this thing we can simply write down this complete equation here, that is RH is one force in horizontal direction, that is plus in positive direction plus 1.5 kilonewton. So 1.5 kilonewton, there's no other force in x direction, so that's why this is equal to 0 as per our condition of equilibrium. So that from this equation we'll get RAH is equal to minus of 1.5 kilonewton. So this is what our first part that we got here from the first equation. Okay, so we are going to use the second condition now, that is sum of all forces in y direction is equal to 0. Now in this case also just observe the forces which are there in y direction and simply list out all those forces. That is RAV in positive y direction, that is RA vertical plus RA vertical, that is second force minus 1 kilonewton, then third force is this one, and second it is minus 1 kilonewton, fourth force is minus 1 kilonewton, then this RBV which is in positive y direction, so this is positive RB vertical, and as per our condition of equilibrium these all forces should be equal to 0. So this is what our second condition, and from the second condition we got one more equation as RA vertical plus RB vertical is equal to minus 1 minus 2 minus 3. Minus 3 will go this side and that will be plus 3. So this becomes our equation number 1, because here there are two unknowns, so that will not be able to calculate this value from the single equation. We need one more equation. So now there's one more condition remaining, that is moment about any point is equal to 0. Now when I'm going to apply this moment, as this is the stable truss as we have calculated and tested it earlier, stability condition, it shows that it is a stable truss, so that's why we can use any point of application for this moment. So any fixed point we can consider. So generally this moment condition should be selected, that is here I'm going to write down some notes also. This moment condition we should use where maximum unknowns are there, or the point of application should be chosen where there are the maximum unknowns. Even if you are going to take it maximum unknowns, this is not hard and fast rule, but if you take it that way, that is fine. So now if you see, there are the n number of points where we can take this moment. Either it is a, point B also we can fix, point E also we can fix. But if we are going to fix up this point B, then there are no such unknowns here, because for this truss 1, 2 and 3 forces will be there in equation when we are going to use this point B. Okay, so suppose if I am going to use this point A, there are two unknowns, that is RAH and RAB. But out of that RAH also, this RAH if you have calculated, now once again there's only one, means one unknown, and at point E also there's only one unknown. It means what, any point we can select now, because whatever the options available with us, there maximum unknowns are only single, or one unknown is there. Okay, so now suppose I'm going to use point A as a fixed point. So always I just have discussed, or I just have told in my previous lectures also, that whenever we have to calculate this moment, always keep these two things in front of you, that is moment. One is sign convention, and another, the formula for moment is nothing but force into perpendicular distance. So always check out which is the fixed point and accordingly take all those things. Now in this equation I have selected this point A as the fixed point. Now I have to take all the moments of all forces visible. So before taking these moments, always whatever the forces which are passing through that point, moment because of that forces will be 0. So we need not to take that moment because of that forces. Okay, so first thing, moment, in moment equation there will be moment because of 1 kilonewton, this 1 kilonewton, this 1 kilonewton, 1.5 kilonewton and RBV. So first of all, taking the moment with respect to this point A. I always suggested that draw line of action of the force. So this is how I have drawn this line of action for this force. Then to get this perpendicular distance only I'm going to draw, or this is the simple method I have shown, but either way you can directly detect the perpendicular distance. You need not to draw this line of action. Okay, so first of all, draw this line of action. This is what our fixed point, right? So from this fixed point, now draw perpendicular on this line of action. So if I'm going to drop down this line, so this will be my perpendicular distance for this force of 1 kilonewton. Okay, and this 1 kilonewton force can be shown this way also. It means what? Now here, whenever I'm going to write down here the equation, the force 1 multiplied by, we have finalized that this is nothing but our perpendicular distance. Now you can go into this figure and check out what the distance is there, because in this figure itself you may get confused. So that's why I've drawn this complete figure at the side by side. So this is what my first point, and this is the line of action of this force, and what we have finalized is the perpendicular distance. So this is the perpendicular distance that we need to know here. So for this force 1 kilonewton, there is the perpendicular distance of 4. So it means what? This 1 into 4 multiplied by, and this is the magnitude, and its sign convention, it is going to create clockwise moment, that is in this direction. So that's why we are going to take it positive. It means what? First moment we are done. Now similar way we can calculate the moment because of this second force, that is nothing but the 1 kilonewton force. Now once again I will draw the line of action for this 1 kilonewton force here. Actually my figure is bit not scaled, so that's why it is the, so this way my line of action is this thing, and this I'm doing just to get a perpendicular distance, because students get generally confused with the perpendicular distance. So I need to just use this method again and again, but once you get habitual for this, you need not to apply this step, or you need not to use this method. So as of now, if you see, this is nothing but our perpendicular distance for this line of action of this force. It means what? I can show this force in downward direction. So for this, from this diagram we come to know, for this force of 1 kilonewton, this is our perpendicular distance, that is A to C, and that is nothing but the 4 plus 4, 8, and magnitude of force is 1 kilonewton. It means what? In our formula now we can use this as 1 into 8. Okay, and sign convention for this moment, see what moment it is going to create. It is going to create in clockwise direction, so that's why this clockwise direction we have assumed as positive. In some books it is negative also, so in order to get confused, always follow any one sign convention. So this is about the second force. Then third force also we can use, that is line of, and now I will directly show that line of action over here. So for this third force, my perpendicular distance is this one. So force and its perpendicular distance is 4 plus 4 plus 4. It means what? 12. So force of, for the force of 1 kilonewton and perpendicular distance 12, so again it will also create a positive moment only, so that's why it is positive. Then check out for this 1.5 kilonewton. Once again, to calculate moment, force will be 1.5 and its perpendicular distance, that is line of action. Draw its line of action. So this way I will simply draw the line of action here for this 1.5 kilonewton, which is passing through that force. That is what called as the line of action. And then from the fixed point, A is our fixed point, so from A to this line of action drop the perpendicular, that is, this is what our perpendicular distance in case of this force of 1.5 kilonewton. So here that perpendicular distance is nothing but 4. So if you draw this line of action over here, this distance will become 4. Okay, and it will also create, so we have to assume that this point is fixed and this is free end. So if by the application of this force, it is going to create this clockwise movement only. You may, okay, so it is going to create a clockwise movement. So you can simply write down, for the force of 1.5 kilonewton, perpendicular distance is 4, and sign convention for this is also positive. Then for the force that is vertical direction, in vertical direction, this is what one more force remaining, the line of action of this force. So this is what our line of action of this force, and perpendicular to this line of action from this fixed point. So this is the perpendicular on this fixed point. Okay, so this is what the force, and this force is acting in upward direction. So now if you see, if something is there which is free at one end and which is fixed at point A, and if you are going to push this thing in upward direction, definitely it will rotate in this anti-clockwise direction. Okay, so this is what going to be minus. So for this we are going to take it as minus of RB vertical multiplied by perpendicular distance. Now for this force of RBV, perpendicular distance will be, our RBV is acting, so not RBV, that is not actually RBV, that is RE vertical. So here also we need to make that changes, RE vertical, and here also it should be RE vertical, and here also it should be RE vertical multiplied by the perpendicular distance for this RE vertical is 4 plus 4, that is 8. And why this sign convention minus? As it is going to create anti-clockwise direction moment, so this anti-clockwise we are going to take it as negative, so that's why it is equal to 0. Now sorry, it is minus, and this is equal to 0 as per the condition of equilibrium. Now all these forces we have just listed. Now simply simplify this equation and get any one. Now in this equation only one unknown is there, that is REV, so that it means we can get this value. So I can simplify this equation as 8 into RE vertical is equal to, I am going to take this side this way, 4 into 1, 4 plus 8 plus 12, 4 plus 8 plus 12 plus 1.5, that is 6. This is equal to, so that RE vertical is equal to, RE vertical will become, that is 4 plus 8 plus 12 plus 6 divided by 8, so it is 3.75. So we got this final value for RE vertical as 3.75, and it is in kilonewtons. Once we get this value for RE vertical, as now we are done with this, all these three conditions. We applied this summation f of x, summation f of y, and moment about any point equal to 0. In that also we got RAH and we got REV and RA vertical and RA vertical and RE vertical. So once again we can simply put up this value of REV in equation 2, put REV in equation 1, so we get, that is RAV plus REV, that is equal to 3. So RAV is, we have to calculate REV we just have calculated 3.75, that is equal to 3. So we'll get value for RA vertical as 3 minus 3.75. This is equal to minus of 0.75. Okay, so these are the values that we got here. So for this RA reactions we got here, so all these reactions, that is RAH, this is one, RA vertical, that is last one we have calculated now, okay, and RE vertical. So these are the three reactions we have calculated in our second step. So in second step We have calculated reactions at all supports using condition of equilibrium for whole truss. Now it is the third step. When we are going to apply this third step, that third step is select a single joint, select individual joint and apply condition of equilibrium. Okay, in the same way here also there's one trick. So individual joint we have to select and we have to apply condition of equilibrium. That is, joint we should select, or the joint should be selected in such a way that where there are the minimum unknowns. So joint should be selected in such a way that there are the minimum unknowns. So once you decide which joint we have to select that joint and apply this condition of equilibrium. So the joint, after selecting that joint, we'll be getting concurrent force system. So here we are going to use the condition of equilibrium for concurrent force system, that is summation of all forces in x direction equal to 0 and summation of all forces in y direction is equal to 0. So always keep in mind, whenever it is coplanar force system and non-concurrent coplanar system like this, in that case we will have to use three conditions: summation f of x, summation f of y, and moment also. But when we are going to use concurrent force system, now we will see what exactly and why we are going to use this concurrent force system to calculate this one. So once again I will put up this diagram in front of you. Once again I will keep this diagram in front of you. So now here, see, I will first of all draw all these forces and or these points and their free body diagram. So individual joint we have to select. So first of all I am going to list out point A. Okay, so if I'm going to list out point A, the free body diagram, when I'm going to draw that free body diagram, in that free body diagram I will have to show force in member AB, force in member AC, reactions which are acting at A, that is vertical and horizontal. So all these forces should be shown over here. So for that I will simply take this force diagram, that is force in member. Here I have to show force in member AC. Okay, then once again I have to show reaction acting at this point A. This is the vertical reaction, horizontal reaction acting at point A, and then force in member AB. So first thing, you can simply show all these things: force in member AC, then force in member AB, reaction, vertical reaction, horizontal reaction. Now I will simply draw the free body diagram for all forces. Now if you see, in our next step, select the individual joint and supply condition of equilibrium, and joint should be selected where minimum unknowns are there. Now if I am going to select this point A, how many unknowns will be there? If I am going to select this point A, there will be FAB which is not known, FAC which is not known, RAB we have calculated, RAH we have calculated. It means what? In this total for this joint there will be 2 unknowns and 2 known. So now for this joint, now once again same way we can check out whether less than 2 unknowns are available in at any other point or not. So if I'm going to select point B, there should be force in member AB, there should be force in member BC, there should be force in member BE, and there should be force in member BD. It means what? If I'm going to draw free body diagram for this point B, then in that case I have to show all these forces.